Welcome everybody to this talk, which is now going to be more about methods rather than governance. And so topic is cloud brightening. Before I report on what models can tell us about the feasibility and the efficiency of these schemes, I would like firstly focus a little bit on the role of clouds in the climate system. And what you see here is the Earth energy budget. With a bunch of arrows and branches in there. So we do have sunshine, and then part of that solar radiation is absorbed either the atmosphere or a lot of it at the surface, and about 30% of it gets reflected. So what's reflected and not absorbed in the atmosphere leads to cooling. So if we can enhance what's been reflected in the atmosphere, then we can thereby cool the atmosphere and balance processes that we do on the other end. So this is terrestrial radiation emitted at the surface, and only a very small part of it has been emitted out to space directly. Most of it, as you know, is absorbed by greenhouse gases, but also clouds, and produces the greenhouse effect that leads to a lot of warming at the surface. So if we were to change the albedo of clouds, make them more bright, then we could try to cool our planet and try to offset some of the warming that we cause by increasing greenhouse gas concentrations. Key here is that in this energy diagram, clouds appear 3 times. So if you only change the reflectivity of clouds, then you are missing these 2 other properties and processes that clouds perform. So they absorb terrestrial radiation and so therefore affect the greenhouse effect, and they redistribute energy within the atmosphere and cause effectively an energy transfer by evaporation, which takes a lot of heat that is then released when clouds form. Clouds form in particular locations, and then this can have a strong impact on the circulation that we see. And so circulation changes might be something that we do not want to achieve if we just purely want to cool the planet as a whole. So radiatively, clouds have 2 effects. And here are a few numbers. So I've told you 30% of the solar radiation is not absorbed in the climate system, but reflected back to space. And over 2/3 of that is done by clouds. So clouds are kind of a good entity in the climate system to tamper with, because if you just kind of get a small change in the reflectivity of clouds, that can have a significant absolute change in the energy budget. So clouds are really important in this reflectivity, and that leads to cooling. However, they're also very important to absorb terrestrial radiation that's emitted at the surface, and that then tries to cool our planet again and kind of emit back to space what we absorb otherwise in solar radiation. And if clouds absorb this terrestrial radiation, they contribute to the greenhouse effect, same thing that greenhouse gases do, so this leads to warming. So if you tamper with clouds, you really want to make sure that this happens and this does not happen. Luckily, if we look at the net effect, so these are really 2 large numbers, so a lot of cooling, a lot of warming, the net effect overall is cooling, minus 20 watts per square meter. If you compare that to the forcing and warming by greenhouse gases currently, which is slightly over 3 watts per square meter, so then that is, again, a significant number relative to the greenhouse gas forcing that humans do. But the issue is that not all clouds cool, so there are certain clouds that are more relevant for cloud brightening than others. In addition, so clouds redistribute energy in the climate system. So if they form, they produce a lot of heating in the atmosphere. And if then that cloud condensate, if that cloud does not re-evaporate, but precipitates out, then you have a net heating of the atmosphere. There are regions where this happens preferentially, And so this is a main driver for atmospheric circulation and the whole hydrological cycle that we see in the atmosphere, also very important for the monsoon circulation in the tropics. So whatever you do with clouds, you have to keep an eye on this so that you don't produce side effects that are unintended. Since clouds energetically or just kind of have huge contributions with opposite signs, small changes can cause significant changes and change the warming estimates that we see due to an increase in greenhouse gas effects. So clouds are quite uncertain, but there are a few general rules that you can make out and that you can use to then pick the clouds that you want to use for cloud brightening. And that one of the major effects is shown here. So if you have high-level clouds, cirrus clouds high up in the atmosphere, they have a much lower temperature than the Earth's surface. There's a high temperature contrast, which leads to a large greenhouse effect. Typically, they're optically relatively thin. They consist of ice particles rather than liquid droplets, so their reflectivity is rather low. So cirrus clouds tend to warm the climate and do not contribute to the overall cooling that we see on average by clouds. So we really don't want to change, make these more prominent. Deep convective clouds, thunderstorm clouds, they are essentially radiatively neutral, so they're also not particularly good to temper with, but the prime type of clouds that produce a lot of cooling and where cloud brightening schemes are targeted for are the low-level stratiform clouds where you have a small temperature difference between the surface, the cloud, so that makes the greenhouse effect relatively small and the albedo effect, relatively speaking, larger. So low-level clouds is what you want to look at. But there are other effects that determine if a cloud cools or warms the climate. So we had already seen altitude. In addition, there are seasonal changes and changes as the part of the diurnal cycle. During the night, there is no sun, so you will only have a greenhouse effect during the night. So we really don't want to have more clouds during the night because that will produce more warming. They can only cool during the day when there is sunlight to reflect. Similarly, seasonal changes in mid-latitudes, as you probably know from own experience, where we are, clouds tend to warm climate during the winter and tend to cool the summer. So again, you have to make sure that you do the cloud brightening at the right time of the year to have a good effect. Then there are microphysical properties, so the properties of the cloud droplets themselves, and this is essentially the main property that we use for cloud brightening. If we have, for the same amount of liquid water, more but smaller cloud droplet, then that cloud with the same liquid water but smaller cloud droplets will be more reflective. So that's the cloud brightening effect that you want. You want to do this with liquid droplets because ice crystals do reflect a lot less, so there's a smaller effect. And then you want to temper clouds that are susceptible to albedo changes, so that really when you increase the droplet number concentration, that also then the albedo goes up. And there are a few rules that thinner clouds are more susceptible and those with a low cloud droplet number concentration are more susceptible. I'm going to tell you, motivate why that is on the next slide. And also you want to avoid non-precipitating clouds because they are essentially, you do have a sink of cloud water. So if you just kind of start to change them, then essentially you're changing precipitation rather than the albedo. Another important factor if you want to select certain clouds for cloud brightening is the underlying albedo. So if you take away clouds and you have a high albedo surface like ice or desert, then essentially the reflection that you got by the cloud is still going to happen, but it's just happening at another place. So equally, if you increase cloud brightening, It's most effective if you do this over a dark surface. So because then you avoid, by producing additional reflection by clouds, you avoid that additionally reflected radiation gets absorbed elsewhere. Oceans are dark, so what we want to do is target low-level clouds over the ocean that are where you have low seasonal changes, a lot of solar input. So it's typically cloud brightening areas are picked in the tropics over oceans, and we target low-level clouds. Okay, so here, brief summary of the strategy. So we seed marine stratocumulus stratus, so these are these layer cloud that you see in the background. Cumulus clouds are those that are dynamically in contact with the surface. So if you add sea salt particles, for example, that act as a cloud condensation nuclei, you have a transport mechanism in the atmosphere into the clouds, so that what you kind of emit as additional cloud nuclei will then really affect the cloud above. Then hopefully that will increase the cloud droplet number concentration, increase cloud albedo, and if you avoid this problem of cloud precipitation formation, then you will have an overall cooling effect. This precipitation formation is an issue here because not all cloud condensation nuclei will get activated to a cloud droplet in the same way. So there are those that are activated first. The rule of thumb, if you have the same type, let's say all sea salt aerosols, if we're over ocean and we have lots of sea salt that we can use, then the larger sea salt particles will be activated early, and the smaller ones might just not form a droplet at all. So if you do the wrong thing and you just kind of add only very relatively large sea salt particles, then you might even make your cloud darker rather than brighter, because the large sea salt particles will form cloud droplets preferentially and large, so that if you do things the wrong way, then you will not increase the cloud droplet number concentration even with more cloud nuclei. There are then other benefits that people are really after, and that is if you have more cloud droplets that are smaller, then the formation of precipitation is delayed, so that might increase the cloud lifetime, cloud cover, cloud thickness, and that gives you further cloud albedo increases and is significant and important for the overall efficiency of your scheme. I'm looking for time, but I don't see a timer here. But anyway, so this is kind of a summary of what you want to do. So you have clouds that are less reflective and they are not too thick, so that you still have some solar radiation that goes through, so that if you increase the reflectivity, you reduce the solar radiation that goes through and can be absorbed further down and go up. But if you want to do that, then there is really a very complex number of processes at bay. So it's not only forming cloud droplets, but they also grow, and then there is a lot of cloud processing, precipitation. They do interact with radiation, so their vertical structure changes, less radiation comes through, so this also changes the structure of the atmosphere below and might affect the moisture transport into the cloud. So although the primary thing is this, produce smaller and more cloud droplets for the same cloud, a lot of other things can happen, and they can be important, as I will try to demonstrate in the second half of my talk. So this is what we want to do. Is it effective? And there is geoengineering model intercomparison. So these are schemes that are relatively large scale. So models can be used to check this out. I really have only 6 minutes left. Okay, so and a number of global models have been used, and in the UK there's a long history for these schemes, and there is a study that was published 2 years ago to look into that, and so they pick oceans in the Pacific. They do avoid a nice region that would be possible in the Southeast Atlantic, because that changes circulation, because it's a localized forcing, and there in their model the Amazon rainforest dies off. So there for hemispheric sea salt emissions, and they find out that this is the first result, so that the optimum size of the sea salt particles that they add to the clouds is less than 100 nanometer. That's about a factor of 10, one order of magnitude smaller than the natural emissions. And then they tune the emission rate such that they keep a high emission scenario to a moderate emission scenario. These numbers here mean that by the end of the 21st century, there is a 4 watt per square meter difference in forcing. So they have a very complicated model. They have aerosols, they have cloud microphysics, chemistry, and so everything interactive. So that's essentially one of the most comprehensive global modeling that have done this study. And what they find is that essentially the emissions that you need to bring the high emission scenario down to a moderate one increases significantly over time, and that non-linearly. So until 2075, you need a few teragrams, but then 25 years later, you need already 400 teragrams, which is about 10% of the natural emissions. So you can achieve something initially. The other big result is that if you go to these high emissions, then it's essentially the sea salt particles which make the sky white. They reflect solar radiation, and so it's essentially not cloud brightening that cools the planet, but it's the reflection of solar radiation by these sea salt particles directly. In addition, there are a number of side effects, and so particularly in the precipitation fields. So there are a lot of things to look out for. It's not just cooling. One of the things, if we think of the theme of Arctic, of this conference, there is an overcooling of the tropics and a residual warming of the high latitudes. Then the question is, can we really trust our global models? And one of the really big issues is that they act on really coarse scales. So they have grid points that cover 10,000 square kilometer, or the model that I've shown you, even 20,000 square kilometer. And if you look at the cloud field, then it looks a bit like this. So this is a satellite cloud fields. This is a cloud model. And you can see that there are really huge differences. Which means one of the big problems that cloud models have is that just by design, they cannot represent individual clouds and processes that form these. So we need much higher resolution models to find out if they're really telling you the truth. The number that I told you, what is their confidence? And so I've done some studies by using observations and the stratocumulus field, observations of a polluted and clean marine environment. And in that study, they found that in the polluted environment, they have smaller cloud droplets, so aerosols lead to cloud brightening. What they, however, did not take into account is that the atmospheric conditions change at the same time, and they couldn't really distinguish between changes in atmospheric conditions and the aerosols. But you can do that in the model, and I did that with a PhD student almost 20 years ago. But I think research there are more of these studies, but essentially they deliver this similar results. So here, instead of 100 kilometer in a global model, we use 100 meter, and then we can resolve processes that lead to cloud formation. And then we have a radiation that interacts with the cloud microphysics, so we can see how then changes in cloud brightness change the dynamics of the cloud. And so we compared observation with the model, and just kind of briefly, we do get the correct water content. So cloud base 1.5 kilometer, this is a 300 meter thick cloud. We do get the right cloud droplet number concentration. And so then we look at the simulated aerosol effects by keeping the metrology the same, atmospheric conditions the same, but just changing the aerosol. What cloud brightness do we get? And we do get, and so here are the observations, point here and the bar. So very large error bar. So we, in the model, we just kind of have more constrained conditions, so we can see we essentially make the droplets 50% smaller, and that leads to cloud brightening, makes them more reflective. In addition, I told you they should live longer. and then you should see more liquid water, but you don't. So the solid curve is the unperturbed, and then the more aerosols is the dashed curve here. And so more aerosols lead to less clouds. So that's something that's definitely not in global models. And it happens because you have thinner clouds and you have less clouds. And dynamically, that happens because you entrain more air from above. And that means that essentially you have a process that leads to warming. Dynamical change lead to warming. Cloud brightening to cooling, the dynamical change can lead to warming and offset the efficiency of what you're doing. Problem is that that is situation dependent. And so you can't really come up with a simple rule. I need to summarize. Question: can we replace observations with model? Answer is a good yes and no. They're extremely helpful tools and they're really cheap. You don't have to implement something. And they tell you that, well, you can get some cooling, but that is probably only going to be a small fraction of what we do today. So there is a limit to the efficiency to it. There are large uncertainties and high resolution models can help. There's more work to do. And in particular, we need observations to then validate the model. So we have to progress with our research on both fronts, the modeling and the observations. And with that, I finish. Thank you.